Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in pretty much any college mathematics course, please consider subscribing and then checking out our playlist and watching videos and then liking, commenting, and sharing those videos. Those are very simple, free interactions that you can do, and they all greatly help our channel to grow. So please go ahead and do those things. All right, in a previous video, I talked about the closure of a topological space. What I want to do in this video is I want to just prove a couple of really simple properties. First and foremost, recall that the definition of a closure of a set in a topological space is the intersection of C, all of the C's, where C not only contains A, but it's closed. C closed is equivalent to saying its complement is open. So it's the intersection of all closed sets that contain the set A. Here are the four properties that I want to prove. The closure is in fact closed. I did actually justify this in the previous video, so this is going to rehash that. But just in case you didn't watch that one and you know what the closure is. The closure is, of course, closed. A set A is always contained within its closure. A is closed if and only if it's equal to the closure. And then fourth, just to verify that if I don't just keep doing iterations of closures, I don't get anything new. If I take a closure of a closure, it does nothing on top of the closure itself. So the closure of a closure is the closure. Sounds kind of silly, but again, otherwise, we could have this hierarchy of I take a set A, and then I take its closure, and then I take the closure of the closure, and then the closure of the closure of the closure, and then we just spiral out of control. That's the way it worked, that's the way it would work, but luckily it does not. Let's go ahead and prove these four statements. 1. The closure is closed. Well, remember that, and I happen to mention over here, I said that C was closed, and then down here I said that the complement was open, right? So if the complement is open, that must mean that the original set is closed. So that's the relationship between open and closed sets, is that they're complements of each other. What I can do is let's actually take the complement of a closure. A closure complement would be the intersection of the set C, where A is contained in C, and the complement of that is open. And I'll take the complement of that. The complement of an intersection is the union of the complements. Again, for the same collection of C. So where C contains A and the complement is open. Well, down here it says that the complement is open, and therefore this is an arbitrary union of open sets, which means that the complement of the closure is an open set, and in particular that says that the closure is a closed set, which is what we were trying to prove. 2. A is always contained within its closure. Well, A is the intersection of sets, all of which contain A. Therefore, if I say let X be an element of A, then X is also an element of C, where C is a superset of A, which means that X is an element of the intersection of all of those, which is equivalent to saying X is an element of the closure, and therefore the set A is contained within the closure. Okay. 2 more assertions. Let me pause this, and then I will prove those. The next statement is that a set is closed if and only if it's equal to its closure. Well, first and foremost, let's prove this direction of the equality or the equivalence. If A is equal to A bar, then since the closure is closed, A is closed because they're the same thing. On the other hand, if I prove the other direction, assume A is closed, then remember that the closure A is the intersection of the closed set C, where A is contained in C, and of course C is closed, or equivalently its complement is open. Well, amongst that collection of C's, A is one of them. So this is going to be equal to A intersect the intersection of C, where A is a proper subset of C and the complement of C is open. But A is in fact a subset of all of these. In fact, it's a proper subset of all of these, and therefore this is equal to the set A. Therefore, the closure of A is equal to A. Okay? And then finally, 4, that the closure of a closure is equal to the closure. Well, the closure is closed. We've established that. And what did we also just prove? That a set A is closed if and only if that set is equal to its closure. Well, what I'm going to do is basically just take statement number 3, and in place of A, I'm going to put a closure. So the closure is closed, meaning, or therefore, the closure is equal to the closure closed. And there we go. Okay. So there's 4 basic assertions along with their proofs for properties of closure of a set. Thank you for watching, and please consider subscribing.